I will be talking about calorimetry in this video. Just a heads up that calorimetry tends to be a more math-heavy subject, so you'll probably see more numbers and text in this video than in others. Before we can talk about calorimetry, we have to go over a heat exchange term. The one I'll be talking about is specific heat capacity, also known as just the letter C. Now, the unit for specific heat capacity is listed here. This may be hard to interpret, but it means the amount of energy needed to raise 1 gram of something by 1 degree, either Kelvin or Celsius. The idea behind specific heat capacity is that different molecules or elements have different responses to heat. Let's take a look at the specific heat capacities of water and steel. Water has a specific heat capacity of 4.184, meaning that you need 4.184 joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius, or Kelvin. On the other hand, steel has a specific heat capacity of 0.466, meaning that you need 0.466 joules of energy to raise the temperature of 1 gram of steel by 1 degree. So, let's say I have 1 gram of water and 1 gram of steel. If I applied 10 joules of energy to both these samples, which one do you think would change the most in temperature? Take a moment to think about this. Steel would change the most in temperature. It changes almost 10 times as much as water does. And this should make sense. If I left a bucket of water and a piece of steel out on a hot day, and then came back to touch them, the steel should be much hotter than the water. The reason for this is because steel has a much lower specific heat capacity than water, meaning that steel's temperature is much more prone to change than water. Something to note is that you may see molar heat capacity. It is similar to specific heat capacity, but instead of joules needed to raise 1 gram of something by 1 degree, it is joules needed to raise 1 mole of something by 1 degree. Since 1 mole of something is almost always bigger than 1 gram, molar heat capacity is typically larger than specific heat capacity of the same molecule. If you want to convert from specific to molar, turn 1 gram of the molecule into moles, then divide the specific heat capacity by that number. I will leave an example for the molar heat capacity of water. Feel free to pause and look it over. The reason I taught you about heat capacity is because it is used in a calorimetry calculation. Now let's talk about what a calorimeter is. A calorimeter is a contraption used to measure temperature changes in a reaction. If something warms up, we say that delta T, or change in temperature, is positive since the final temperature will be higher than the initial temperature. If something cools down, we say delta T is negative since the final temperature will be lower than the initial temperature. So here's a model of a basic calorimeter. Think of this here as a box inside a bigger box. The space between the two boxes is filled up with a solution, usually water, which I represent with the dashed lines. There's a thermometer here which takes the temperature of the water. So back to our inner box. This is where our reaction of interest happens. As you may recall from the previous video, reactions are either exothermic or endothermic. This means that heat is either required or released. If heat is required, it is taken from the nearby solution. If heat is released, it is released into the solution. Either way, the temperature of the solution will change. It either goes up or down depending on if heat was required or released by the reaction in here. The thermometer allows us to measure this change. So, what's the point of finding this change in temperature? There is an equation known as the Mcat equation, which is closely associated with calorimetry. By finding the change in temperature, you can learn a lot about a substance. You can discover its specific heat capacity, its mass, or the overall heat of the reaction. Now, I want to emphasize something. We talked earlier about what goes on inside this box, that it is either an exothermic reaction or an endothermic reaction. Let's pretend that it is an exothermic reaction. The reaction inside here is going to release a certain amount of heat. that exact same amount of heat is going to move into the water and make it warmer. The big idea is that the amount of heat released inside here will always be equal to the amount of heat absorbed by the solution. Think of it like giving someone money. This may seem like common sense, but if you give someone $5, they will receive $5. Likewise, if this reaction gives out 5 joules of energy, the surrounding solution will absorb 5 joules of energy. The same is also true if the inside reaction is endothermic. If this reaction absorbs 5 joules of energy, the surrounding solution will release 5 joules of energy. We represent this through a simple equation. This equation is a summary of what I said earlier, that the energy released is equal to the energy absorbed, or the energy absorbed is equal to the energy released. Don't worry about the negative sign. It's there because one reaction will cool down and the other reaction will warm up. This leads to opposite heat values, since delta T will be negative for one reaction and positive for the other reaction. To make these two enthalpy values equal, we have to put a negative sign. So that might have been a lot to take in. Try to test your knowledge by answering some practice questions. Refer to the top left corner for equations. Watch out for units and sig figs. I'll reveal my answer, so pause this video while you're working on it. Hope you did well on it. If you have questions, leave them in the comments. That's all for today. Goodbye.